Hi everyone, this is Ginny, uh, Assistant Professor from IT Department. Today lecture is operating system. The course outcomes of operating system is course outcome 1, understand the various scheduling algorithms and process synchronization. Course outcome 2, analyze and contrast deadlock prevention and avoidance algorithm. Course outcome 2, compare and contrast various memory management schemes. Course outcome 4, understand the functionality of file system, IO system and virtualization. Course outcome 5, compare iOS and Android operating system. Unit covered in Unit 1 introduction, Unit 2 about process management, Unit 3 about memory management, Unit 4 about storage management, Unit 5 about virtual machines and mobile operating system. In the today concept is deadlock. In deadlock concept, we have system model, deadlock characterization, methods of handling deadlock prevention, deadlock avoidance, deadlock detection, and recovery from deadlock. So this first one, deadlock. So what is deadlock? So first one, deadlock problem. Before going to see the problem, what is deadlock? A deadlock is a situation in an operating system where two or more processes are waiting for each other's resources and name of them can proceed. In some simple words, if you are waiting for me, I waiting for you. Then simple example. In process P1 has resource R1 and needs R2. Process R2 has resources R2 and needs R1. Now R1 waits for R2. R2 waits for R1. So in this slide we have two system has two drives, two tape drives. P1 and P2 each hold on to a tape drive. Each needs another one. For example, semaphores A and B initialize to one. Then necessary condition of deadlock. Uh, Here one for one example, bridge crossing example. Traffic in only in one direction. Each section of a bridge can be viewed as a resource. If a deadlock occurs, it can be resolved if one car backs by preempt resources and rollback. Several cars may have to back by if a deadlock occurs. Starvation is possible. Then system model. System model resource types R1, R2, resource 1, resource 2, up to resource some. CPU cycles, that is memory space input devices. Each resource type RA has WA instances. Each process utilizes the resources follows request, use and release. Then deadlock characterization. Characterization is deadlock and characterization means identifying and describing the conditions under which deadlock occurs in a system. In mainly example, the four necessary condition, the resource allocation graph. First one for necessary condition, that is mutual exclusion, hold and wait, no preemption and circular wait. First one, mutual exclusion. A mutual exclusion is one process at a time can use a resource. That is, at least one resource must be non-shareable. Only one process can use it at a time. Then hold and wait. Hold and wait is a process holding one resources while waiting for another. It's at least one resource is waiting to acquire additional resources held by other processes. So third condition is no preemption. So no preemption is a resource cannot be forced by removed. They must be released voluntarily. Then fourth one is circular wait. Circular wait, chain of process exists. Each process waiting for a resource held by the next process. In the three axis set of process 1 and process is 0 of waiting process, such that waiting for a resource that is held by process 1 process 1 process 1 is waiting a resource that is held by process 0. So P2 up to P n minus 1 waiting resource that is held by. So this is a circular wait. If any one of these condition is removed, deadlock will not occur. Then resource allocation graph. Resource allocation graph, a set of vertices and set of edges here. Mainly the resource allocation graph is used to describe deadlock graphically. The components circle of O, that is process, square, that is denoted as resources, arrow from process, that is resource, and the request edge, arrow from resources, process allocation edge. Then the important rules of resource allocation graph is there is a cycle in the graph. For single instant resources, deadlock exists. For multiple instant resources, deadlock may exist. Here a request is directed H P1 to RJ. Assignment H directed H RJ, PJ. In the resource allocation graph, RAG is directed graph, or P and R in the set of consisting of all process in the system. There is having request edge and assignment edge. Then resource allocation graph. A resource allocation graph is a directed graph. That is resource type with four instance. PA request instance of RJ. PJ is holding an instance of RJ. Next one, example of resource allocation graph. So resource allocation graph is a direct graph. G equal to where vertex comma edges, vertex comma edges, where V equal to set of vertex and E equal to set of edges. So which it's used to, so which process is requesting a resource, which resource is allocated to which process. Vertex we are divided into two types. Process set P1, P2, comma P3. The process set P is P. These are a process in the system represented by cycle of 0. Example P1, comma P2, comma P3. Then the resource set of R, that is these are resource type represented by rectangles. Examples R1 equal to printer, R2 equal to scanner. Then edges E two types. One is the requested directed edge from me. The for the meaning of this is process P1 is requesting resource RJ. Example P1 comma R1. P1 wants R1. Assignment edge, directed edge from meaning resource, that meaning is resources RJ is allocated to process PI. Example R1 comma PA. R1 is given to P1. Then resource allocation graph with a deadlock. Then resource allocation of deadlock, that is we have R1 and R3. R1 in resource 1 we have process 1, process 2. R3, that is resources 3, we have holding process 3. Then resource allocation A cycle with no deadlock. The diagram shows R1 resource 1, resource 2. So in the resource 1 process 1, and resource 1 P2, process 3, process 4. Then basic facts. So basic facts is a graph contains no cycles, that is no deadlock. Yeah, if a graph is having a cycle, if only one instance per resource type, then deadlock. If several instances per resource type, possibility of deadlock. Then methods of handling deadlock. So, why the deadlock prevention? That is, deadlock can be handled using for four main methods. One is deadlock prevention. So, prevention of deadlock system for entering deadlock by eliminating at least one of the four necessary conditions. Eliminate mutual exclusion, eliminate hold and wait, eliminate no preemption, so eliminate circular wait. Then the system checks before allocation whether gaining a request will lead to deadlock. User safe state concept. Then deadlock detection and recovery. that is allow this is deadlock prevention, that is the system from entering deadlock by eliminating at least one of the four necessary conditions. Mutual exclusion not required for shareable resources, must hold for non-shareable resources. Then on hold and wait, must guarantee whenever a process requires a resource does not hold any other resources. Request process to request can be allocated is the resource before it begins the execution, or allow process to request resources only when the process has none. Low resource utilization, starvation possible. The next one is deadlock prevention. So deadlock prevention is the prevent the system from entering deadlock by eliminating at least one of the four necessary conditions. Uh, if a process that is called some resource requires another resource that cannot be immediately allocated to it, then all resources currently being held as are leased. Preempted resources are added to the list of resources for which the process is waiting. Process will be restarted only when it can regain its old resources as well as the new one that is requesting. Then circular waiting involves a total ordering of all resources types, then encourage each process requires resources and increasing order of enumeration. Then deadlock avoidance. Deadlock avoidance requires the system has some additional prior information available. The most useful model requires each process declare the maximum number of resources each type that may be need. The deadlock avoidance algorithm dynamically examines the resource allocation, examines the ensure that it can be never be circular weight condition. Resource allocation state is defined by the number of available and allocated resource and the maximum demands of the process. Then safe sequence. Safe sequence is the safe sequence is on order of process. That is, we have process 1, process 2, up to process n, such that each process can get its remaining needed resources and finish. After a process finish, uh, it will release its resources. Those resources become available for the next process. For here is safe statements no deadlock. Unsafe statements may lead a deadlock, not necessarily deadlock immediately. For example, suppose we have available resource equal to 3. Process needs process 1 needs 2, process 2 needs 1. Save sequence. Give 1 to process 2. Process 2 finish releases resources. Now total equal to 3. Give 2 to P1 to P1 will be process. Then basic facts. Already I told if a system is in safe state, there is no deadlock. If a system is unstated, possibility of deadlock. Avoidance. Ensure the system will never enter unsafe state. Here is the diagram, safe, unsafe, deadlock state. Here is the deadlock. Unsafe means safe state means when a process requests an available resource that must decide to immediate allocation, allocates the system in a safe state. That is uh, a safe sequence in order of process. Then resource allocation graph algorithm. Climates P1 indicated that the process request resources represented by dashed line. Climates converts to request states when a process requires a resource. When a resource is released by process assignment, it reconverts to a climate. Resources must be claimed a prior in the system. Resource allocation for deadlock avoidance. And this diagram, resource on resource 2, process on, we have resource on, process on to show the resource 1 and process 2, resource 2. Then unsafe state and resource allocation, the diagram representation in resource 1, resource 2, process 1 and process 2. Thank you.